So our third talk of the day is by Octavio from CIMAT, and just note that we swapped the Friday 11:30 talk with days. Okay, thank you.
Yeah, thank you very much, and thank you very much for the invitation. This is the first time I come to Western University. It's very nice. Today I will talk about second order cumulants. I will talk about a paper with Jamie Mingo on what we call second order even and second order Ardional elements. But so the idea is that so basically the paper wants to put more examples in the framework of second order freeness and to be able to calculate a lot of things. Because somehow we had the impression that maybe many people were not interested in this theory because it was hard to actually put their hands in there. And with this paper, we show that actually you can do a lot of things. So maybe I will review first order versions of what I will talk in the second order level, which is these Ardional elements and what we call even elements. So just maybe I will repeat a lot of things that were said before because I'm not assuming that all the people is here or taking all the courses. Just a reminder that we work in a non-commutative probability space, which is just an algebra with a linear functional that sends 1 to 1. We will work with basically limits of matrices, so we can assume that we are in a sister algebra. So this is positive. And just a reminder that freeness is just a rule to calculate mixed moments. And since we will talk about random matrices, I just recall that one of the two examples which are important is that if we take two Gaussian, say GOE or GOE, maybe for this talk you should have in mind GOEs because this is the theory of second order freeness is based on the unitary invariance and not orthogonal invariance. So if we have this, they are asymptotically free, meaning that in the limit, the joint moments are calculated as the joint moments for free random variables with the specific distributions. And another very nice example is that if we have two, say, deterministic matrices, meaning they are, the entries are not random, but they have limiting distributions, then if we rotate one of them, then this new version, which is rotated with the original one, is asymptotically free. Particularly, I can take A to be B. Okay? So the idea is that randomly rotated or things which are in general position, somehow they lose all the relations and then somehow they become free. Okay? And we have seen yesterday and even today in the morning these transforms and these cumulants, which are just, I just take the Cauchy transform. I take its compositional inverse. I subtract the pole at 0. And then I get this R transform, which has these cumulants. And the classical, not the classical, the usual moment cumulant formula, free moment cumulant formula. Here it should be. Yeah, because I'm forgetting the cumulant one. Yes, sorry. This is what you're saying, right? Yes, sorry. Okay, but then we have this moment cumulant formula, which just says that if you can calculate a moment in terms of these cumulants. Okay. And this is the multivariate case, which is just I take any functional on a product. It is just the sum of the non-crossing partitions on these over all partitions, and then how to calculate this. This is just the product of the cumulants on the entries. Okay, this is just a reminder. If there is any question here, I suppose not, then I can continue. And one of the things that was shown yesterday in or mentioned yesterday in Peilung's tutorial was that mixed cumulants vanish, meaning that if I have elements in two algebras and I have a cumulant which has at least two guys in different algebras, then this is zero. And I am repeating many things because then I will say the second order version of this, which will be just exactly the same by putting a second order function. One thing that I will use, and it's very useful, is suppose I have products of a cumulant on products. This need not be free. I can actually calculate the cumulant of the product. This is the formula for products as entries by just summing over certain partitions that satisfy this relation. So let me just explain with an example. Suppose I want to calculate the second cumulant of A1, A2, and A3, A4. So I need to consider all the partitions such that one of the blocks connects this A1, A2 with A3, A4, meaning that one block should be in the third or fourth and in the 1 or 2 entry or second entry. Okay, so for example, I can take the whole partition, give me this A4 of A1, A2, A3, A4. So the point is I can, to get a formula of the joint moments, joint cumulants of these in terms of the individual joint cumulants. Okay, so this is, I take 4, one block. I take one block on A1, and then the other block connects the other 3. Okay, and so on. So these are all the blocks that connect these two with these two at these ones. Okay, not all the partitions of size 4 appear here. They should have this condition, which is exactly this in terms. Okay, and now what if they are free? Okay, so if they are free, right, I need to use the previous result that cumulants which have at least. So I am assuming that A1 and A3 are free from A4 to an A4. Okay, so this is this one. Sorry, this one vanishes because it has at least, for example, A1 and A2. So this vanishes. This vanishes because it has A3 and A4. This vanishes because it has like A1 and A4. Right? So at the end, after this big formula, many of them vanish, and we have only actually 2 guys. Okay, when they are free. So I'm using both the formula for products as arguments, and that the joint cumulants vanish. Okay. Yes.
There are no terms with kappa 2 squared, right?
There's no kappa 2 squared because there is no.
Yes, there is.
Kappa 2 squared, sorry.
Kappa 2 A1 4.
This one.
That's the old one. What is with kappa 2? I don't know. A1. Okay, we're crossing.
The other one, the other possibility is 1, 2,
Yeah.
4, but that would satisfy the superposition size.
Yeah, so if I have
Okay.
kappa 2 A1 A2 times kappa 2 of A3 A4,
Yeah.
This will connect this part with this part. Yeah, yeah. So at the end I get this formula for the product of free random variables. So if this one is free with this and this one is free from this, I will get this simple formula. Okay, so it takes some work to actually calculate this kind of thing, but one can do this. And in fact, there's a formula for if I have A1, A2, A3, A4, and so on for any, and it's just this formula that appeared with the Carrera's complement. Okay. This should be A1, A3. Okay, I also had the same problem as Jamie that had some problem with the indices because I also did this yesterday night. Okay, so the formula that I was mentioning was exactly like this. Helps me, for example, to calculate what is the moment, the cumulant of AB It's just the sum over all partitions, and then I take the Kreyer's complement. Okay. And how you one way to prove this is exactly using these two. One is the moment the formula for products as argument, and the other one is vanishing of mixed cumulant. Okay. Now, the two objects that I want to analyze today is this called Ardional Elements, which satisfy. So they have. I am in a star algebra, and I have A and A star. So what I do is I assume that the cumulants, the only non-vanishing cumulants, are the ones which have A star, A star, A star. Otherwise, this is 0. So I'm talking about the joint cumulants between A and A star. Okay, so this is another way to say what is the joint distribution between A and A star. I'm not assuming that A and A star are that A is normal or self-adjoint. This is actually a non-self-adjoint element. Okay? So I'm providing the joint distribution somehow in a strange way if you are not used to free cumulants. Okay. And another one, which is maybe more natural, is I just take a symmetric distribution. This gives an even element. So this is just that the odd moments are 0. Okay, and you will think that this is there is not much relation, but actually the combinatories are basically the same when you want to look at A star or at A square. And two examples which are we should have in mind is this semicircular operator and this circular operator. So semicircular is just the central limit theorem, gives just the Catalan numbers. So it's an element whose moments are Catalan numbers in the even moments, and the odd moments are 0. Okay, and what is a circular operator? This is just I take this semicircular and I add I times another free semicircular, and you will see that it satisfies this relation easily. Okay, and
in that case, you mean the distribution would be like the whole,
yeah, the distribution of this, the Brown measure of the circle is a disk, and it's related to this Kirchhoff's law, yes. Kirchhoff's law. So you should have in mind that the Kirchhoff's law, the circular law, or you can attribute it also to other people in random matrices mathematician, but the physics literature is called Kirchhoff's law.
it's a full circle.
Yeah. Yeah, but here we're thinking of S plus I S2 when they are free.
Free
and semicircular. Okay, this is, and one can calculate the joint moments.
You can prove this using R transport.
What can I prove?
Can you prove the distribution is disk using R transport?
You need bigger machinery. So if you want to calculate the distribution of this, I will look at more general Ardional Elements, which is the paper of Hagerup and Larsen. I don't know if this is correctly, sorry. Maybe double S. Yeah. Okay. And all these the distributions of these are actually symmetric, rotational invariant. So this is very nice operators. Okay. And another example is Haar unitary, which is just exactly not the disk, but in the circle.
How do you define it?
You can define it in terms of moments. You can.
So how do you define it?
So this is just a unitary. Okay, such that phi of u to the n is 0 for all n in n. This is a Haar unitary. Yeah, you should have this distribution. Yeah.
Negative powers as well.
Yes. If you want to put, okay, maybe I put this. Okay, but it follows.
But when n is 0, it's supposed to be 1.
Okay, yeah, but okay, yeah. And the Bernoulli is just 2 points, -1 and 1. So I want to argue that they are more or less similar objects. One is like the rotational invariant version of the other one. Okay, and the reason is that actually one can calculate the distribution of the square of an even element. And what is very nice is that it's only like you use a moment cumulant formula. You see, this is the moment cumulant formula, but instead of this alpha, which are the cumulants, you only take the ones which are non-zero. And for R diagonal case, it's exactly the same. But then you take the only ones which are not zero. Okay, so this was done by Andonika and Roland Speicher in 1997 in this very nice paper. And the idea of the proof is actually use the moment, this moment, or this cumulant as entries. Yes?
Yeah, so usually you have this formula that you have alpha on the left-hand side and you sum of all non-crossing of kappa. But now it's different, right?
Yeah, these alphas are not the same alphas as Jamie's.
Okay.
So these are just another cumulants, which are these cumulants.
These are the classical cumulants?
The free cumulants. I'm talking about free cumulants. Here you will see kappa and k. They are the same. Free cumulants.
So here they're the same. It's not your K.
No.
Okay, sorry.
I use the convention kappa equals k. Yes. Yes, you will see a lot of typos there anyway.
That's a formula which says how to express the equivalence of x squared in terms of those of x.
Okay.
That's exactly what it says. Okay.
Exactly.
And for x, you just take the even ones because it's even. The odd ones.
Exactly. And also this is saying how to calculate the cumulants of A star in terms of the cumulants of A and A star, which are the only ones which are not zero, because I am assuming that this is an R diagonal operator. Okay. And the nice thing is that this is really nice formula. It's just like the moment cumulant formula. Okay. And the idea of the proof is just this formula for products as arguments. So the formula for products as arguments says you want to calculate the cumulant of a product A star. Then what you need to join, this is what they're saying, you always need to join all of these guys.
There's one sequence code that there's just one A star without an A. Testing.
Yeah, here there is an A. Huh? Okay. Okay, and the point here is that if you want to do this, okay, you want to join blocks, all of the blocks. And the observation is that actually if you look at one element, you cannot go to the next A, because then this guy will be alone. Okay? So basically what you need to do is so if you go to one A, you cannot go to the next A star. So actually, if you have one A, you need to go to the next A, right? Always, if not, this guy will actually, I'm going forward, we'll see this guy and it will separate these two parts. Okay, so the only possibility, so this is what I'm saying, that this is separated from the rest, and then you won't satisfy this subcondition. Okay, the only possibility is that this guy goes with this guy, and then this guy goes with this guy, and then you see, I put it there, that was missing. Yeah. Okay, so each guy should go with the next guy. This is one condition, and if he satisfies this condition, then you can do whatever you want. Okay, and how do I finish? Well, I just choose a partition now, not on the A's, but on A star, right? So you make like another partition, and what you get is all the partitions. So basically, what I'm telling you is which are the partitions which satisfy this sub under these two conditions. One is that the cumulants should go A star, and the second one is that I need to satisfy the sub partition. And this is the proof goes. But then one realized actually that I didn't use actually that A should go to A star, but I only need parity. Okay, so you don't care if this is an R-diagonal element or if this is an even element. This is the same argument. That's why you have the same formula for both. So the combinatories are exactly the same. Okay. Good. And actually, there's a way to get from a even element, you can get an R-diagonal. But actually, there's this theorem that says that if I have any R-diagonal element, say U, or sorry, a hard unitary times any operator, this is an R-diagonal element. But vice versa, any R-diagonal element can be written as a product of a hard unitary and another element. And with this, you can show that the product of R-diagonal elements are actually R-diagonal elements. Okay, and actually, you can calculate, for example, the distribution of the product once you know the ones of each one. And there's a way to go from an even element to from an R-diagonal element to an even element, but just constructing a 2x2 matrix, which is just like the usual Hermitianization trick, right? So what you do is you put here your R-diagonal, and then you put here the star, and you will get an even element. So actually, I guess you can cook up another proof of these formulas by just using this amplification trick. Okay. Okay. And so now I want to go to the second order level and try to see if I have an analog of R-diagonal elements and even elements.
Sorry, I forgot what R-diagonal element was.
R-diagonal element means that the only joint moments between A and A star, joint cumulants, are these. Okay, and then maybe you ask me, why do you care about this? I hope that at the end of the talk, I will give you enough examples so that you care about these guys. This is the only non-zero, and the other K2n of A epsilon 1, A epsilon n is 0 if they are not on this form or vice versa.
Thank you.
Sorry. Yes. Okay, so I'm checking the time. So second order freeness, as in the talk before, cares about covariance, the limit of covariance of traces of powers. Okay, so I care about K2 of traces of powers. And we assume that it has a limit, meaning that if I normalize correctly, this guy goes to something. And I assume that the higher order cumulants go to 0. Okay. What Jamie put it here was that he assumed that if I multiply by n to something, this goes to something. In particular, this should go to 0. Okay. So I don't care about the higher order freeness. I only care about second order freeness, fluctuation moments. Okay. So I care about these guys, which is just the covariance. Okay. So the framework that the algebraic framework that tries to deal with these guys is this second order probability space, which is I have the original one, and I add this tau 2, which, as explained by Jamie, sends L1A and A1 to 0. Okay, and this is bilinear, symmetric, and tracial in each of the entries. Okay. And the moment cumulant formula for the second order version is just the sum, which here I explain. So basically, we have two types of diagrams. The first ones come in this form. This is called NCN, and it's just I need to have one block which is in both sides, like this one. And the other type is basically I have two partitions, one in each side, and I connect them. I don't know how to do this annulus trick version by Jamie. I just connect them directly. You can do it always, actually, by rotate them. Okay.
This would give a kappa 2, 2.
This will give a kappa 2, 2, And then the rest is just first order terms. Okay. At least one true block, and this has no true block. And as you pointed out, this has a kappa 2, comma 2. Okay, these are the first formulas that already we saw in the last talk. Some of them have second order things, and some of them have only first order things. Okay, and I hope I did this. I think this is also incorrect. This should be. No, this is correct. Okay, so this is the R transform. This is the second order R transform. And we have this formula for the relation between the second order R transform and the second order and first order Cauchy transform. Okay. And now I want to do the same as before. Okay. So we have that mixed cumulants vanish. This was the theorem that we used. And the second thing is how is it related to random matrices? And again, these two examples are actually second order, asymptotically free of second order in the limit. So two examples important. Again, I have deterministic matrices. I rotate one of them. And Gaussian matrices, complex Gaussian matrices are, I mean, GUEs. Okay? And the point maybe is that, okay, I know this. Can I calculate more examples? Once I know a GUE, can I calculate, for example, the product of 2 Ginibris or the product of 3 Ginibris using this machinery? Okay. Yeah, this is the whole point of freeness. Like if I have two things which I know, can I calculate, for example, the sum or the product? It's not about one matrix, it's about one matrix built from other matrices that I know. And this is the idea. Okay. And we have a similar formula for products as arguments, which again, I will explain in a picture. Okay. Yes. So I will work with abstract examples, but they come from this tau 2, which is here. Oh, as in Jamie's talk, exactly.
That was just reminding me that that's what formula. I had it wrong in my slide. I was at a second part. Cauchy transform one.
Here. Okay, good.
I need to after.
Okay. Sorry, did I answer the question? Yeah. Exactly. So you should think this as this is built to model random matrices, and this should model the limiting distributions. The point is that once you know that the limiting distributions are second order asymptotically free, you can put this machinery abstractly. So this is an abstract algebra. Okay. So this was the formula that Jamie showed. And this is like the moment cumulant formula in a functional version. Okay. And the point, yes, is that we can try to do examples. And one thing that was mentioned in the last is that general Wigner matrices are not asymptotically second order free. Okay, so one should be careful. Okay, and this is the formula for products as arguments. And what it says is a little bit different. It doesn't say you should join blocks, but you should separate the opposite. Okay, so basically what we have is that we have some points, which, so here you have the variables A1, A2 to AN, and then the next one. And what you need to do in this second order version is that you should separate these points. Okay, so for example, this is not separating these 2 points, meaning they should not see topologically. There's a definition which is more precise with permutations, but at the moment this is enough. Okay, and then I have again this definition of what is an R diagonal second order free, second order R diagonal element. So it is a first order R diagonal, means this satisfies, But I also assume something about second order cumulants means exactly that. Only the even second order cumulants of the form AA star, AA star, AA star, or the form A star, A star A are non-vanishing. Okay? And one thing that is actually not obvious is that the hard distributed, so meaning I take the limit of hard distributed in UN matrices in the I take the hard measure on the unitaries, and this is asymptotically a second order R-diagonal element. And another one, which is more simple, because I know as Jamie mentioned, is that the only second order cumulants of a Gaussian, actually they are all zero, because they're only K2 in the first order is zero. So it's trivial that this actually guy is second order R-diagonal, because I already know that this is an R-diagonal, and the second order thing is just obvious. It's just, yes. Yeah, but here I am in the trivial case. So I will assume everything is trivial. So in that case, both of them are the same, even in the first order level. Yeah, we're modeling matrices, which should be trivial. Yeah. Another question? So these are, again are two the main examples. We will show that there are more examples on how to build them. This is the idea. And an even element is just as before. So we have these moments which are zero, and also these moments are zero if P plus Q are not even. Okay. And again, the semicircular operator should be not only semicircular in the first order, but also have fluctuations as the limiting object of the GUE. Okay, we can do actually relate them, right? But then we have so the first theorem is that if I have two R-diagonal elements of second order, the product is also an R-diagonal of second order. So in particular, since a circular operator is like the limit of a geometric ensemble, if I take the product of them, then this will be an R-diagonal operator. So just by proving this, I am telling you a lot about the joint cumulants of the product of the geometrics. I am just saying that you should only look at the cumulants of the form AA star at first and second order level. Okay. And again, if I have a second order hard unitary and A is the limit of a deterministic, then the product with a hard unitary, which is second order free from A, is also an R-diagonal element. Okay, so what I'm saying is that examples that we usually treat in the first order level also work in the second order level. Okay, and again, I have a formula for the cumulants of AA star in terms of the cumulants of A and A star, which is again, these are the only ones which are not zero. Okay, and then I took, what is this? This is actually the moment cumulant formula of second order level. So in particular, I have this formula between, so another functional relation between the cumulants of A and A star and the cumulants of A star. Okay, and here there is a main difficulty is that R-diagonal elements behave very nicely, but even elements are the definition of this determining sequence should be different, because this trick that I got from A to A star doesn't work in the second order level. So I need another definition for the second order determining sequence, which I need to add this guy, which is maybe it's not so important what is here, but the most important thing is that not all the combinatorics are the same if I take even elements and Ardional elements. Okay, but again, once we have this definition, we can prove this formula for the square. Okay, and the main difference is that, as I mentioned before, the argument was that if I go from A star to A star, this guy won't be separated. But this guy is valid because, sorry, I cannot go from A to A star to A star because this is a second order Ardional element, right? However, I can go from X to X if this is even. And this parity thing topologically these are the same, this is not true in the second order level. That's why we have different definitions for this. So I need to take all the guys which come from these cases and put it together. Okay. And as I mentioned, we have at the end what we get is how to get the cumulants from the determining sequence, which is this B, of the original ones. Okay, and I was rushing maybe a lot because I started late, so I have time for examples, which maybe is the most interesting thing about the talk, if you don't like combinatorics. So the first example is, so we call a second order semicircular. This is the limiting of a GUE. What do we get in the limit? Basically, we get all the cumulants are 0, except, so first order and second order cumulants are 0. And this is proof, this is known, that in the limit you get this, except for K2. Okay, so this is definition of a second order. This is just the limiting of the cumulants of a GUE. Actually, you could define the second order any order semicircular to be this, but you put any order cumulants. The second thing is now I can define what is a free or a second order circular operator. Okay, this is just.
So sorry, statement. What does it mean? Say this object or piece of it?
What I'm saying is that a GUE, if you calculate the limiting covariances, they will be all 0. If you take the covariance of A to the N and
I think that there's no element. There is no element. We're talking about some object doesn't exist, but its moments exist.
so what I'm saying is that the combinatorics of the limiting objects of the limiting joint moments of the GUE can be characterized by the cumulants being 0 except the K2 SS.
I'm sure it can be formulated, but with the current formulation,
If you want an algebra, you can follow one variable, find eight on polynomial by the definition of the moment. Have a moment sequence, but then we'll just say what it is.
so something like what you do in asymmetry.
Yeah. So the first order level, I'm just saying that all the cumulants of first order are 0 except the second one for the GUE. This is just saying that the limiting distributions converges to the semicircular law. What I'm saying is that fluctuation moments are the same as the one who has these cumulants.
I believe this is totally correct. It's just a question of formulation.
Okay.
For outsiders.
Yeah, what I'm saying is that this consider this element makes sense and because it comes from a GUE. And then what I want to play around is now I have two GUEs. And then I want to say I take S1 plus I S2, normalize so that it has variance 1. So K2 of this star. And just by linearity of the multilinearity of the cumulants, then all the cumulants are 0 except K2 of C star. K2 of C with C star. So maybe this is the definition of a circular one. Is all the cumulants are 0 except K2 of C star. Okay. And this is again, I can do if I can do this, I can do this on random matrix theory. Okay, and maybe the first observation is, can I calculate what is a square? Okay, like Wishart. Okay, and here there's a difference if I take a complex one or a real one. So, and this is the calculation. I can actually calculate them using the formulas I did before. This is just the moment cumulant formula, because I know that what is the determining sequence. The determining sequence is very simple. B1 is 1, and then the rest is 0. Okay, and I calculate, and I can get this side. Then I can ask about CC star. Okay, in the first order level, if I take CC star, I get a Poisson, a free Poisson. This is a Marchenko-Pastur. If I take S squared, it's also Marchenko-Pastur. But in the second order level, I get something different, because the combinatorics of even elements and Ardional elements are different. The determining sequence is different, because I need to sum over this second part. So the determining sequence actually of an R-diagonal, a circular, is B1 equals 1 and Bn equals 0, and this is 0. And then what I get is that the second order cumulants of CC star are also 0. Okay, and this was somehow unexpected, because the second order cumulants, the first order cumulants of CC star are not 0. It's very different. Yeah, but here it's also the same. Somehow you cannot connect. You don't have enough space to connect. Okay. So this shows that CC star and S squared have different second order moments. Okay. We can also do products of free elements, and in particular, this is interesting because now we have like a circular operator, which is a Ginevri. We can do the product of Ginevris. Okay, and what we call the product of K free circular operator is just the limiting of the product of Ginevri ensembles. And we have a formula which says that it is just some object which we call the K divisible alternating non-crossing partitions of PK and PQ. Sorry, KQ elements. But actually we have a formula. Okay, so this is the formula for the product of C1, C2, CK, C1 to CK star, and one case was considered already by D'Artois and Forrester, the case where I only take the product of 2 Ginevri ensembles, and this was done using actually topological recursion. We can do general case.
Ginevri was definition was normal.
Yeah. But they are not Hermitian, and it should be complex. Complex. He means Gaussian, not normal in that case.
What do you mean? I mean, a normal matrix is something that satisfies A star equal to A star A.
Sorry. Is Gaussian.
They have Gaussian.
Oh, I see.
Square matrices without any symmetry.
Just all the square matrices. Complex
Square matrices. Yes. Complex entries independent and Gaussian. Or normal.
Yeah, Gaussian entries.
I think this there is an ensemble which consists of normal matrix. No, not Gaussian. A star A star.
Well, so usually once you throw in, okay. So imagine parts are in probably enough. I mean, for 6 diagonal.
The Ginevri would be just complex Gaussian.
Yes.
Yeah.
So so people is typically interested in these fluctuation moments, because this is actually a self-adjoint element. But actually we can calculate not only this, but all the joint moments or the joint cumulants of this guy, which is not self-adjoint, which is saying much more. saying what are the star moments. What I'm saying is that the only non-vanishing second-order star cumulants are exactly these ones. The rest is zero. Okay. Yes.
And they conjecture just for k equal 2 or for any?
They conjecture for k equal to what was this formula, but they don't say anything about star.
Also have for calculation of 25K. They landed their conjecture.
Yeah, but and another, I think, which is an interesting example is if this is related to Wishart ensembles. So one is typically interested in this kind of, you have a Wishart matrix, you multiply by something and then you multiply by W star. Okay, and you want to know what is the distribution. We can also calculate the second order moments. And actually, this is more general because we don't need to assume that this is deterministic. Okay, so we have this formula that the cumulants of CAC star are the moments of A, and independent if they are second order free. Okay, so this is as in the first order case, the moments of CAC star are the cumulants. The cumulants of CAC star are the moments of A. Okay, so one particular case, which is exactly when that comes from random matrices, is when A is deterministic. In that case, the fluctuation moments are zero. Right? If it is deterministic, the fluctuations are zero. So this means that in this formula here, okay, this part is zero because this is the only thing appearing in the second order level. So actually, we have a formula between for the Cauchy second order Cauchy transform of CAC star in terms of the first order Cauchy transform. See, there's no R there. Okay, so this is the place where this vanishes. This is zero because second order cumulants are zero. Okay?
Sorry, by deterministic, question. By deterministic, you mean system is not.
So you have the entries are not random.
You just take one.
You take one matrix, but maybe you do like a sequence of matrices. Maybe you want to take the same spectrum if you want. Yeah, so this is deterministic means the entries are not random.
So if you want to make
You can take any matrix, but this is exactly the same because we are rotational invariant. So this is general enough what Jamie said. Okay. So yeah, so the point is that we can do very specific, explicit calculations of these second order cumulants and second order moments with this machinery. Okay. Just to finish is that not everything is nice. For example, in the first order case, we have that if R is Ardional, R to the N is also an Ardional. I'm not taking a product, but R to the power. And this is not true for the second order level. Okay. And another thing is that there is this very nice thing that in the first order level, if you conjugate with a unitary, which is free, then this is free from A. And this is not true in the second order level, even if they are second order free. Okay, so there are some things that are not so nice, so one should be careful. And maybe I can stop here. I hope this was interesting for you.
Thank you. Any questions, any comments? Yes, please.
Can you go back to the definition of the second order R diagonal free cumulant?
Second order R diagonal.
Yeah, R diagonal. Yeah, here. What happens if you have A star, then you have it P times, and then you have 2 times A star A. So the
This is Yes, sorry. This is also not this is the same. This is also non-zero.
It's also not zero. Okay.
Because I didn't say it because we were in the threshold case.
So you can have a trace in the first block. So in the first
Yeah.
block,
Sorry. Yes. That's why I didn't put it because we're in the threshold case, so it's the same. You can rotate.
Okay.
Yes. No. I can only rotate at the level at the 2p.
Yeah.
I can rotate.
The first block and the second block.
Yes, I can especially. This is the same. Yes.
Just a question about any equation or equivalent.
The thing is that we don't even have the distributions for us is just moments, joint moments. And maybe the question is if I can formulate this in terms of second order moments. And I think we don't have a nice description. I don't know. I don't have a philosophical reason. So we did a calculation. We tried to prove that R to the something was, and we realized that even the hard unitary to some power is not an R diagonal. We actually calculated the fluctuation moments of U a hard unitary to some power. We do this on explicitly. And the second thing is, this one is also a calculation, but actually, the thing is that one reason that one expected this was if you have, as I mentioned, if you have a deterministic matrix and you rotate randomly with another deterministic matrix, they are second order free. So this is somehow the analog, but you need more things because you need somehow more information of what is to be independent, and it was not clear for us what do you need.
On the other side, putting a box around that off. Other particles. So that's wrong. Have a block across. Doesn't curve it. Well, I order that cross circle. Because it's sort of like don't put a roof on it. Put out some walls. Side, but you can't hop on the line, you can't hop over the wall. This is logical.
Yeah, that's the combinatorial reason. Maybe from the random matrix point of view, I think it's not clear what to assume on U and A that is not everything is free. Yeah.
We know like both not diagonal elements. Right. Then like so like God like
So we know that the U times B is an R diagonal because the product of any hard unit, any R diagonal with anything is an R diagonal. So you're asking about the converse, that if any second order diagonal can be written in this way, and we tried, we didn't get too far because you need really to work on the relation between the polar decomposition. So this is.
There is a probability, there is some other probability where as right? Because you're allowed to just manufacture some other space.
But you want them to be free.
Second order
free, right?
Right. So I don't find that, but it would second order product with some.
Yeah, I tried. Maybe you should have tried.
Model. It's like that's pretty.
So my answer will be, we don't know. And the main problem that I think is positivity. We don't know what positivity is in second order thing. This is my answer. Apart from maybe Jamie has this in. Yeah. Yeah, exactly. Positivity. Yeah. If you want to do analytic things, you need somehow positivity, and this is a problem.
How many scenario?
Any other question from our audience on Zoom? Have any questions, any comments?
Yes, I do have a question.
Sure, go ahead.
It is known that all diagonal elements maximize the non-microstate free entropy. So I wonder if there is a second order free entropy theories in which that the second order all diagonals do the same thing.
Yeah, this is a good question. I think there is, for the moment, not any free entropy, either microstate or not microstate approach. There is nothing.
Okay. All right. Thank you.
Any other questions on Zoom side? Okay, then let's thank Octavio. We will have lunch break. We'll come back at we will start the Zoom meeting afternoon. The talk of Zoom, the first talk. Yes. And for the lunch, well, there are a few options around. So Grad Club is still there. You all know that Grad